Our next presenter this morning, presentation is entitled Determining Flumioxazin Dissipation and Effects on Peanut Using a Thermal Gradient Table. And our speaker is Kayla Eason.
All right, well, thank you for that introduction. Like he said, my name is Kayla Eason, and I'm currently a PhD student at the University of Georgia. And today I'll be presenting on determining flumioxazin dissipation and the effects on peanut using a thermal gradient table. So Georgia peanut producers have a limited number of herbicide options available to them, with about 23 active ingredients and 9 modes of action listed below. And of those 23 active ingredients, Valor or flumioxazin is one of the more commonly applied herbicides in peanut, with 65% of the peanut hectares in 2018 having flumioxazin applied to them in the major peanut producing states shown on the right-hand side of the screen. Valor or flumioxazin weighs 354.3 grams per mole and is a protoporphyrinogen oxidase or PPO inhibiting herbicide that controls multiple weed species, including Florida beggarweed, morning glory species, common lamb's quarter, and prickly sida. Microbial metabolism is the main pathway of soil degradation for flumioxazin, while hydrolytic degradation is the main pathway of degradation in water, with its half-life varying greatly depending upon the pH. For Valor, it's applied pre-emergent in peanut, and it is a 51% active ingredient applied at about 107 grams of AI per hectare typically. While some growers do see Valor injury early in the season, especially with unfavorable weather conditions, it is still a very popular herbicide. And with this injury and earlier planting dates and new cultivars being released, little information was available to us on the effects of pre-applications of flumioxazin on the peanut seed. This led to a study that was recently published in the paper Hurdle et al. 2020. The objective of this study was to determine peanut seed radical response to flumioxazin as a factor of germination using a thermal gradient table. The materials and methods included using Georgia's 16HO and flumioxazin concentrations ranging from 0 to 100 parts per billion, with the seed placed on temperatures ranging from 20 to 29 degrees Celsius. Here, differences in flumioxazin stability between temperatures were evaluated using a regression model that fit flumioxazin concentrations and determined the radical length on the y-axis in millimeters and the temperature in Celsius on the x-axis, and describing the different slopes of the line from this regression. There were no differences. Thus, flumioxazin did not impact radical growth as a factor of germination. But from this and from the determination that flumioxazin concentration over temperature and time did not impact radical growth, we still had the question of why. Why did we not see any changes or impacts? So this led to another study with the objectives being to determine the temperature effect of flumioxazin in an aqueous solution using a thermal gradient table, and to determine the activation energy of flumioxazin. Our two hypotheses were that temperature was directly related to flumioxazin dissipation, and that the Arrhenius equation would be able to describe the activation energy of flumioxazin. Our thermal gradient table's construction is 2.4 meters long by 0.9 meters wide and 7.6 centimeters thick. It has 24 temperature columns with 9 cells per temperature as depicted by the red box. And fluid flows across each side of the unit from either a cooling or a warming unit depicted by the red arrows. And the thermocouples are placed under the table in holes measuring 8 millimeters by 7 centimeters deep, allowing for the thermocouples to be 5 millimeters from the table surface in 10 centimeter intervals. A flumioxazin sample solution was prepared as a stock solution with buffered flumioxazin and water. 100 milliliters of this stock solution was then transferred into 250 milliliter flask, which were then placed on specific table cells according to their respective temperatures. And then 1 milliliter aliquots were collected at each sample date and placed into HPLC vials, which were then stored at -10 degrees Celsius until analysis. The flumioxazin concentration used was 100 parts per billion, or 0.282 micromoles per liter, as I'll describe it throughout the rest of the presentation. The temperatures ranged from 11 to 40 degrees Celsius, with there being 4 replications per temperature, and the sample collection timings were from 0 to 336 hours. So data analysis included multiple steps, the first being exponential decay. For this, data were analyzed using a nonlinear regression in SAS 9.4 to determine whether the response could be described by the exponential decay equation shown. And then data were graphed in sigma plot 14 to determine the first order rate constant, or K value, which is then used to determine the half-life. The half-life was graphed in sigma plot 14 using the equation T of 1/2 equals the natural log of 2 divided by that K value. Finally, for the activation energy, this was graphed in sigma plot 14 using the Arrhenius equation shown here. And the Arrhenius equation represents the magnitude of the rate constant as a function of activation energy, which is that EA, over the average kinetic energy, which is the RT. The activation energy is a threshold energy required by the reactant, or in this case, flumioxazin, to reach its transitional state. And then once in that transitional state, the reactant, or flumioxazin, begins breaking down into products, or degradants. And then a higher activation energy requires more energy to reach the transitional state, while a lower activation energy requires less energy to reach the transitional state. Here are my LCMS methods used for determining flumioxazin, and all samples were analyzed using a Waters Acuity UHPLC ARC system, coupled with a Waters 2998 PDA and a tandem Waters QDA mass spectrometry detector. Before moving on to the results, it is important to note here that data were combined over 2 experimental runs. So starting with a regression of flumioxazin concentration in micromoles per liter on the y-axis to incubation time in hours on the x-axis for each temperature, the initial concentration is 0.282 micromoles per liter. And this allows us to establish that first order rate constant, or K value, which we'll then use to determine the half-life and activation energy. In this graph, each of the dots represent a sample mean for each sample date at each temperature, and the error bars represent this, the standard error. Here are the K values for each specific temperature received from this graph. And here we take those K values and plug them into our half-life equation, giving us the half-life of flumioxazin for each respective temperature, ranging from 11 to 40 degrees Celsius. We can graph those half-lives, with half-life being on the y-axis and temperature on the x-axis. And again, we see that the half-lives range from about 65 to 9 hours. It is a wide range of half-lives across temperatures. And from this, we see a direct linear relationship between temperature and flumioxazin half-life in that aqueous solution, meaning that as temperature is increasing, we are seeing a decrease in flumioxazin half-life. So to accurately characterize temperature effects of flumioxazin stability on a thermal gradient table, the Arrhenius equation expressed as a natural logarithm was used. The variables needed to solve the Arrhenius equation are K, our first order rate constant, A, our pre-exponential factor, EA, the activation energy, what we're going to be solving for, R, our universal gas constant, and then finally T, temperature in kelvins. So we have to transform our temperature and K values into the appropriate units needed for the Arrhenius equation shown on the screen. And from here, we can determine the Arrhenius diagram for flumioxazin in the aqueous solution with our natural log of K on the y-axis and 1/T times 10 to the negative 3 on the x-axis. This graph gives us an R squared of 0.87, and it helps us determine our A, or pre-exponential factor, of negative 7,017.9. Our first step in solving the Arrhenius equation is to convert A from joules to megajoules, which is shown here. And then our second step is to solve for the EA, or activation energy, which the activation energy was determined for flumioxazin to be 58.35 kilojoules per mole. So in summary, our flumioxazin half-life that we determined in the aqueous solution ranged from 65 to 8 hours at 11 to 40 degrees Celsius. As temperature increases, molecules move faster and collide more vigorously, increasing the likelihood of rearrangements, thus increasing the rate of dissipation, which describes what we saw. For our activation energy, here are our results for flumioxazin, which are with our half-life at 25 degrees Celsius being 1.7 days. Similarly, primsulfuron has a similar half-life and a similar activation energy, while halosulfuron shows that because it has a higher activation energy and requires more energy to reach the transitional state, it has a much higher half-life. We did meet our first objective of this study, and we did meet our second objective because the activation energy of flumioxazin was established. Our hypothesis, we do fail to reject the first one, and we do fail to reject the second one. Going back to the first study that started the second study and determining why we didn't see any impact on the peanut seed radical length, it's a multi-part answer. The first part is we determined the half-lives for the temperatures used that were 61 to 29 hours. Here's a table of the estimated flumioxazin concentrations 10 days after initiation, and this is based on flumioxazin dissipation only and does not include the rate of metabolism. At 10 days after initiation, when the peanut radical seed length was determined, the 29-degree temperature, the dissipation did reach 8 half-lives, which would mean that concentrations would have little to no activity. Another part is that flumioxazin dissipation after further evaluation could be described as biphasic, having a faster dissipation from 0 to 100 hours than 100 to 336 hours. Also, peanut seed is able to metabolize the flumioxazin. Coupling these two factors together helps us describe why the peanut seed radical length was not affected by the various flumioxazin concentrations over temperature and time. For future research, we want to evaluate flumioxazin dissipation and effects on other peanut cultivar types, and then also evaluate flumioxazin dissipation in soil, comparing those results to our results here. We'd like to determine half-life information for both phases of dissipation and further evaluate the biphasic nature of flumioxazin, and also evaluate pH effects of flumioxazin in tank water in solution. And a small thing that we learned is that we initially used a pH of 8 to 9 and saw rapid dissipation, but then we prepared a new solution with a pH of 5, which is what we used for this study. And this is similar to previous research, just showing that here flumioxazin degradation was inversely related to the pH. And also in Florida, flumioxazin is used in more than just peanut. It's used in aqueous herbicide control. So it is important to know what the pH of your water is, because you could be losing herbicidal efficacy simply by using a high pH water to fill the sprayer. And here's a list of my citations. And then my acknowledgements. I'd like to thank my co-authors, sponsors, and committee members and support staff. And then with that, I'll take any questions.
Thank you, and very nice presentation. We have one question at this point. It's from Dr. Peter Dautre. How would the soil persistence of 3 ounces of Valor change if used in West Texas soil pH 8.1, overhead irrigation, 100 plus temperatures versus when used in Georgia in days? All right, so I'll repeat that one more time. How would soil persistence of 3 ounces of Valor change if it was used with Peter Dautre in Texas, where the soil is 8.1, overhead irrigation, 100 plus temperatures versus how it's used in Georgia in terms of number of days?
So with the question being the differences in basically flumioxazin stability and use in the soil between Georgia and Texas. And while we do have some similarities, we definitely are very different on a lot of fronts. And with Valor, flumioxazin, there's a lot of factors that would go into that. First off, the 100-degree weather, we'll see it here as well. And that does impact it, but I think the pH of the soil is a little different than the pH of the water solution that you're using in the tank. So you would lose herbicidal efficacy if you used a high pH water source. However, in the soil, it wouldn't be as much of an impact as a direct mix in the tank. But all of that stuff coupled together, you could definitely lose herbicidal efficacy up front. You may still be able to get some herbicidal efficacy out of it, but comparing Texas and Georgia right off the bat, here we would probably see a little bit longer efficacy than they would out there.
Okay. And one last question from Dr. Barry Tillman. Would lower rate of application for early planted peanuts help to reduce injury?
So the question about lowering the rate to help reduce the injury. So wild growers do see injury in unfavorable conditions with flumioxazin. Multiple studies have been done by Dr. Prosco here, also showing that there was no yield impact with those early season damages, unless it is a very extreme case. And the problem with lowering the rate is it's a real balance. So following the label, the lowest available rate to use, you might be losing some of those more, not resistant, but I'll say resilient weed types. You might lose a little bit of control. And then at that point, you'll have to reapply another herbicide, which kind of just adds to more expense, et cetera, et cetera. So it's a real balance. I don't think there's a direct answer to that, but it's a real balance of multiple factors, I think.
Okay, that's the time we have. Thank you very much for the presentation and for the questions.